Hi, in this video I want us to take a look at vector and scalar components. As you know, vectors can be expressed in terms of a magnitude and a direction. What we have here is a GeoGebra applet. In your notes you'll be provided with links to this video and this applet. So GeoGebra has what are called sliders, and so this slider allows me to vary the magnitude of the vector, which in this case represents the velocity. So you have many different types of vectors. Examples of vectors are force, acceleration, momentum, and what we learn here can be applied to the various types of vectors. This slider controls the direction of the vector, which is expressed as an angle measured counterclockwise from the positive x direction. So I can vary the magnitude of the vector and I can vary the direction of the vector. Notice I had to adjust the screen so the vector can be seen in all quadrants. Now we can see the vector moving through all the various quadrants. So I have to make a compromise here. For example, in this compromise the vector runs behind this text box, but I can bring this down, I believe. Okay. So let's take a look at this angle. This angle is measured counterclockwise from the positive x direction. We have a button here that allows us to toggle the angle that is shown over here where the vector is. Notice I can see the angle between the vector and the y-axis, and I can see the angle between the vector and the positive x-axis. So now this number here coincides with this number. So you can play with this. You can just follow the link, either download or work with the applet online. Alright, so let's put the vector in the first quadrant. These vectors are called the vector components of this vector. So what are the vector components? These are vectors which are parallel to the x and y axis and whose sum give us the vector in question. These vectors are parallel to the x and y axis, and the sum of these two vectors gives me this vector. Notice the length of this line and the length of this line, when added, do not give me the length of this line. To get the length of this line in terms of the lengths of these two lines, I need to use Pythagoras' theorem. The sum of these two vectors is this vector, but the sum of these two lengths is not this length. So that's what we're trying to say here. So notice as I move the vector into the different quadrants, the components change direction. In the first quadrant, both vectors are in the positive directions, positive x, positive y. In this quadrant, this vector is still in the positive y direction, but now this vector is in the negative x direction. Now both vectors point in the negative directions. This in the negative x, this in the negative y. And over here, this vector component points in the positive x direction, while this vector component points in the negative y direction. This button allows us to toggle the components. You don't necessarily have to visualize the two components like this, although this is a pretty popular way of doing it. But you could also do it this way. But notice these two vectors still add up to this one. To see it, you just have to move this and slide it down here. We could put it like this also. So these last two ways are not very popular ways of looking at the vector components, but sometimes you might find it necessary to draw them like that. And of course, then we have this way. So this is probably the most popular way of drawing the two vector components, the tails joined together. And notice you can see the parallelogram law here at work. As you can see, the parallelogram rule is saying pretty much the same thing as the tip to tail rule. The sum of these two vectors gives me this, and the sum of these two vectors gives me this. So now let's look at the scalar components. Scalar components are numbers that can be positive or negative. Scalar components are not vectors. So we need to get this distinction very clear. A scalar component is a number that represents the magnitude and direction of the corresponding vector component. So for example, here we have a vector that has a magnitude of 9 and the direction right now is 64 degrees counterclockwise from the positive x direction. This is one vector component and this is the other vector component. This vector would be expressed analytically as 8.09, 90 degrees. And this vector would be expressed as 3.9 meters per second, 0 degrees. Let's just shift the angle here. This vector would be 6.69, 90 degrees. And this vector would be 6.02, notice not negative 6.02. This vector would be 6.02, 180 degrees if we measure the angle all the way from here. So whenever you're talking about a vector, you have to give a magnitude and a direction, or as we shall see later on, two numbers. And guess what those two numbers are? You probably guessed it, the two scalar components. Let's look at the scalar components then of this vector. The x scalar component is minus 6.02. What this is telling us is that the vector component has a magnitude of 6.02 and points in a negative x direction. What this scalar component is telling us is that the corresponding vector component has a magnitude of 6.69 and points in the positive y direction. Let's bring this into the third quadrant. Here both the scalar components are negative because both the vector components point in the negative directions. So the scalar component will be negative if the corresponding vector component points in a negative direction, and will be positive if the corresponding vector component points in the positive direction. Well, notice that these are just simple numbers. To get the magnitude of a vector, you cannot simply add the scalar components. You have to apply Pythagoras' theorem, which means that you have to first square these numbers and then add those squares and find the square root of the result, which is what we have here. So this is the magnitude of the vector v shown here, and it's equal to this expression which involves the scalar components. Notice it doesn't matter if these are positive or negative because they'll be squared. This is representing the vector, and this vector is equal to the sum of these two vectors. So it is very important that you be able to calculate these scalar components. Before we look at that, let's go over a few items here. First, the lengths of these component vectors and the vector itself form a right angle triangle. Next, it should be fairly obvious that these two angles here are complementary. That is, they add up to 90 degrees. Remember that for a triangle, the three angles add up to 180. Since one of them is 90 degrees, the other two have to add up to 90 degrees also. Likewise, these two are complementary. You also need to remember that the sine of an angle is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent opposite over adjacent. When working with vectors, it is best to work with an acute angle that takes the x or the y axis as one side. So let's toggle the angle here. The sine of this angle, 36 degrees, is the ratio of the length of Vy to the length of V. That is, the length of Vy divided by the length of V. Sometimes we use the term magnitude, so it's going to be the magnitude of Vy divided by the magnitude of... We could also work with this angle in here, which would be 54 degrees, in which case now the sine of 54 degrees would be the length of Vx divided by the length of V. So let's say that again. The sine of 36 degrees here, the sine of this angle, is the length of this vector divided by the length of this one. But if we use this angle here, then the sine of this angle is the length of this vector divided by the length of V. With some very basic algebra, we can then use these relationships to then calculate the scalar components. The magnitude of Vx is going to be equal to the magnitude of V times the sine of this angle. And the magnitude of Vy is going to be equal to the magnitude of V times the cosine of this angle. Note, we also need to determine the sign of the scalar. And we do this by looking at the vector component. If it points in the negative direction, then we have to multiply the expression by -1, as we see here. So Vx is this expression or this one. Notice they both give you the same answer. And Vy is this expression or this one. They both give you the same answer. You can also toggle these components if it helps you to see it better. So notice the sine of this angle is going to be the length of Vx divided by V. And so the sine of this angle is going to be the cosine of this one. Cosine of this angle is Vx, the length of Vx divided by V. So always work with the acute angle that is formed between the vector and the x-axis or the vector and the y-axis. Work with the magnitudes of the scalar components and then determine the sign from the direction of the vector component. So that's it for this video. See you in the next one.